All right. Before we get started, just a quick programming note. If you love our brown bags and want more, please ensure that you're on our mailing list. I'll just post a link to that if you haven't got it already. I'll just post it in the chat. If you want us to host something specific for you and your team, whether that be a brown bag, a training, or something else, please get in touch directly at info@eliiza.com.au. Also, just a note to please keep your video and microphone off, but feel free to ask any questions as we go along within the chat functionality of Google Meet, and there will also be time to ask questions over voice at the end. This presentation will also be recorded as well as the text questions that are asked. Okay, my name is Lucas Sargent, and I'm a machine learning engineer with Eliiza, and today's talk is going to be about first principles approach to machine learning pipelines. So this talk will have two main elements, including some theory behind ML pipelines, and then a fun example of one. So for the theory, we're going to cover what are ML pipelines, why build ML pipelines. We'll go through some of the guiding principles when building our ML pipelines and some core design decisions that you'll come across if you ever make your own ML pipelines. For the fun example, we're going to be analyzing talkback radio. Now, these examples are going to be in TypeScript, but don't worry if you don't know TypeScript or JavaScript, because mostly what I'll be showing is just going to be interfaces anyway. Throughout the following presentation, I'm going to use these two icons. So this theory icon and this radio icon to differentiate which slide refers to which, and they'll be in the top right corner of each slide. The idea being that the design decisions to be made will be theory, but the choices that I make specifically for our talkback radio are just an example. And as this is a relatively short first principles talk, we'll be focusing only on the inference side of machine learning pipelines. However, it's worth noting that all of our guiding principles, design considerations, and learnings still apply to the training side too. But before we dive into what an ML pipeline is, we should probably recap what ML is. So ML is an opaque box where data goes in and answers come out. Now, I know the ML aficionados among us will probably be squirming with this abstraction, but the point is that it is just an abstraction, and it's all we really need for moving on to our pipeline principles. It's worth noting that this diagram that I've got here could actually be thought of as describing an ML pipeline. It wouldn't be a very good one, otherwise this talk would be very short, but in a conceptual sense, it is one. So something I'm hoping you're asking yourself, looking at this slide, is of course, answers to what? If our data goes in and our answers come out, what's the actual question that our answers are answering? Well, that's of course going to depend on what your ML system does. So let's take a look at our talkback radio example now. Let's pretend that the question we want to answer is, what's the sentiment of what's being discussed on talkback radio? We can see that our diagram then becomes talkback radio goes in and sentiment comes out. Sentiment, by the way, is just a measure of positivity for a given statement. So if someone said, I'm having a great day, we would hope that would be closely associated with an upper value of 1. But if someone said, I'm finding this lockdown period quite difficult, well, we would expect that to be associated closer to the lower value of -1. Okay, so we know what ML is, and we have the question we want to ask of our data. But what is an ML pipeline? Well, an ML pipeline behaves much like you may envision a physical pipeline to. It still takes in our data at one end and gives out our answers at the other end, but this time we break down that opaque box in the middle into smaller pieces of logic. Specifically, we want these pieces to be replaceable and reusable, along the same lines as a physical pipeline, so that we can replace certain pieces without needing to recreate the whole pipeline if there is something wrong with a particular piece. In general, what we are after is to break out our ML system into modular components. I've denoted here 3 broad types of components. Pre-processing, a type of component that may not contain ML itself, but helps get the raw data into some usable form. Transformational components that transform the data from one logical form into another. And then finally, extractory components. Components which extract specific information from a more general form. But these are really just a guideline. And in reality, you may have many of each. it can be quite difficult to immediately draw the ideal components given any particular ML system. The key point is to move from more general to more specific operations as you progress through your pipeline. It's also worth noting that you can choose whichever scale makes sense for you, from high-level abstract components, as we've got here, all the way down to individual layers of your neural network, although I would generally recommend sticking with broader strokes until you identify some use cases for going smaller. Regardless, let's see what components we might have for our Talkback radio example. So this brings us to our first design decision, determining our pipeline components. Firstly, I mentioned just before that you can go as low level as you want in terms of scale. And although I personally recommend broader strokes with your pipeline, looking at your model can be a really good way to determine some high-level blocks to break into. In our Talkback radio example, our initial non-pipelined implementation was actually a combination of AWS services, specifically their speech-to-text API, followed by their sentiment analysis API. So that gave us the hint that we should probably split these two components out in our pipeline. If, however, your ML model isn't so clearly delineated, it may help you to think about the information that you would need if you were to comb through the data as a human. So in our case, I wouldn't need to listen to hours of radio if I could just read a transcript at my own pace. And that perhaps hints that text is a better form for us to transform into. And then secondly, I thought about how we're going to run this pipeline. And I made the decision to run it with a minutely cadence. So our initial pre-processing component actually focuses on breaking down the Talkback radio stream into MP3 files 1 minute in length, and then recording them with the particular minute that they happen to refer to. Although I could have done a live stream all the way through this pipeline, that certainly adds a lot of complexity, and sticking with a known cadence actually enables us to make some really nice decisions further down the track. Okay, so we've chosen our components, but before we go any further, let's cover off some ML pipeline terminology we're going to need. So we've been focusing pretty heavily on our components, but what else makes up an ML pipeline? Well, we've got an orchestrator, sometimes referred to as a DAG, which stands for a directed acyclic graph. And an orchestrator describes how the components fit together. So this diagram we have here, as well as all the previous ones I've shown so far, actually have components, but they also implicitly describe how those components fit together with the arrows. So this diagram is more accurately a diagram of an ML pipeline orchestrator. And at this point, I'd like to introduce the analogy of a band, where the players in the band are our components, and the orchestrator is the piece of music to be played. And the environment is really just that, the environment the band plays in. The reason I like this analogy is twofold. Firstly, it highlights two distinct modes of orchestration. In a smaller band, we might have it such that all the players, or our components, are trusted to come in at the right time, given the same piece of music. However, in a larger band, we might have a distinct person in charge of orchestration, a conductor. This analogy also highlights the importance of the environment. The environment you choose for your ML pipeline largely dictates which mode of orchestration you will use, as well as which instruments your band members are able to play. Now, of course, our ML pipeline environment doesn't refer to a stage or a theater, but rather the computing environment that our components and orchestrator run within. Whether that be a single process, physically distributed across many nodes, or abstractly distributed with containerization. The environment directly influences the instruments available to the players to play in much the same way that it directly affects what programming languages and libraries you have available when building each component. These are the three big ones. They really make up what an ML pipeline is. Runs and triggers are more just useful terms to understand. So a run refers to a single pass of data through your pipeline, whether that's a run that's currently running or has previously ran to completion. And it implicitly refers to both the input data as well as the version of each component at the time of the run and the actual answer generated by your pipeline. A trigger refers to the event which begins a new piece of data input flowing through your pipeline. It may be a reaction to some external event, or it could just be a run that's recurring on a simple timer. Okay, so now that we know what an ML pipeline is, why do we want to build one? Well, we get all the usual benefits of modularity. So we have clear ownership of responsibility for each component. We're able to individually test, version, and roll back these components. And it gives us much greater code reuse and data caching. Now that last one is probably the most important, specifically for ML pipelines, as it enables us to ask more questions. And I sort of hinted at this at the beginning of our talk, but what happens if the question you want an answer to changes or another question arises? And this is where the real value of ML pipelines come in. We're able to reuse component code, and in some cases, we're actually able to reuse intermediate data to improve the overall throughput of the system and or lower the running costs depending on our environment. As an example here, if this top row is our first question and we gather some answers to it, and then suddenly question 2 comes along, rather than needing to rerun our whole pipeline, we can simply tap into this intermediary data cache and only run this final component. And you can see how this grows as more questions arrive. Okay, let's dive back into our radio example and introduce a second question. What topics are people talking about on the radio? Now, this is commonly referred to as entity extraction, and it generally involves determining the subject of each sentence, the thing being talked about as opposed to the words used to describe the thing. Well, this gives us a new diagram for our ML pipeline. We can see that we've added a new entity extraction component, as well as 2 intermediary stages of data, minutely audio and minutely transcripts, which enable us to run our sentiment analysis and entity extraction components without needing to run our speech recognition twice. The minutely audio intermediary data, although not directly saving us on components we need to actually run, provides a unified view of our minutely audio. That is to say that each descendant component is able to rely on the fact that they are getting the same information within their minute of data. Okay, so we've got our desired ML pipeline mapped out. But before we continue with the next design decision, let's go over some of the guiding principles that we want to follow. Excuse me. So firstly, we've got our components. And whatever components you choose for your ML pipeline, it's important to follow these guiding principles. You want to have well-described and documented interfaces or APIs between your components. You want to make sure that you have agreed points of ownership and responsibility for each component, and you want your components generic enough for reuse as new questions arise. So some ML pipeline libraries and platforms will prescribe the components of your pipeline completely. And this is actually an example of TensorFlow Extended, which does just that. But for a first principles talk, let's keep it simple with just our 4 components. Next up, we've got our orchestrator. When determining an orchestrator, we want to make sure that whatever we choose clearly composes our components. An orchestrator could be configuration-based, or code-based, or described in some graphical user interface. But whatever form it is, we really want it to describe the DAG of our ML pipeline from data to answer as clearly as possible. What I've pictured here is actually an excerpt from my colleague Shin's talk on building ML pipelines, which goes much more into the nitty-gritty of using some of those major ML pipeline platforms and tools. On the right, we can see how a pipeline is composed for TensorFlow Extended in Python, and then below is a diagram of how that pipeline flows visually. Our next decision is the environment or environments. And this is one of the broadest decisions you have. Whatever you choose, you want to make sure that it's easy to compare results across different component versions. If you choose to cache intermediary data, then you need it to support data lineage. And perhaps most importantly, you want to support the languages, toolsets, and libraries that you actually want to use when writing your components. And then last but not least, we want to accomplish all of these things while following general software engineering best practices. So versioning all of our code changes, automated suites for testing, logging, and auditing. We need it to be performant at scale, and as much as possible, we want to use open standards for data exchange. So this is clearly no small task. Just before we dive into the core design decisions that I actually made for the Talkback radio, it's worth mentioning that it's worth calling out that this is a first principles talk. So the idea is not to use existing ML pipelines, packages, or platforms, but rather build an understanding of what ML pipeline tools do under the hood. This is obviously going to enable us to make optimizations of those platforms and build an awareness around some of the implicit design consequences that these platforms actually make for us. But with that being said, ML pipeline packages and tools really exist for a good reason. So once you understand them, I highly recommend finding one that fits your use case and using that. Okay, so with that said, let's continue. We've already made our first design decision, which was our components. So let's make our second design decision. How are we going to orchestrate our components? So I chose to go with what I'm terming intra-container orchestration, where each container knows how to trigger itself, gather its inputs, and pass on its outputs. If we go back to our band analogy, each player is trusted to come in at the right time. This is distinct from inter-container orchestration, where there's some application independent of the components that actually handles the triggering and passing of data in and out, or the band has a conductor. So I guess the main benefit of this method is obviously that it's containerized. It's really simple because we can just use Docker Compose as a runtime for our orchestrator, but the main disadvantage is that the containers are long-lived. So ideally, all your containers should be quite short-lived processes. And what I've got here is actually a picture of our Docker Compose file that describes the sentiment portion of our ML pipeline. So we can see this is the first component, record 3LO, which is given the command to record using the process ffmpeg, and it outputs into an S3 bucket. And then we also pass in the URL of the radio that we want to record and the label for that radio. The second component is our transcribe using deep speech component. And again, we can see that we're giving it the command to transcribe using the process deep speech, where this time the input is S3 and the output is also S3. And the sources specified here is then a combination of the processes that previous data has undergone. So we want this component to act upon data that has been recorded from 3LO with ffmpeg. And then finally, our sentiment analysis component. Again, we're telling it to analyze the sentiment, this time using the natural JS process, where the input is S3 again, but this time we're outputting into a Postgres database. And we specifically want to listen to anything that has been recorded from 3LO using ffmpeg that has then been processed by deep speech version 0.7.3. So our third design decision, how are we going to handle our data? Is each component simply going to pass its data directly to the next component, or is there some intermediary cache? And I guess as I've hinted at in the previous screenshot, I decided to go with direct data lake integration, where each component actually directly gets its inputs from the data lake and puts its output back into that data lake. And then by prefixing the data stored with the processes that that data has undergone and the versions of those processes, you can see that it enables us to support the required data lineage. You can see on the right what these directories actually look like. This is just a screenshot from S3, where each directory contains files that just have the minute they refer to in those directories. I also chose to use standard formats for each piece of data. So the audio directories, such as 3AW ffmpeg or 3LO ffmpeg, simply contain MP3 files. And then the transcription directories, so those are the ones that have been additionally processed by deep speech, just contain JSON files with the transcript within. However, a disadvantage of this method is that each component is actually serializing and deserializing our data. So there is a price to pay with overall data throughput. But for our radio use case, it's really minimal. So fourth design decision, what languages and programming paradigms are we going to use within our components? Now, this decision really isn't as important as the others because our containerized pipeline means that each component could have its own language and paradigms within it. But I chose to keep them all the same just for the sake of simplicity. So they're all written in TypeScript and using a library known as RxJS to provide a functional paradigm that is also event-driven. So this is the same screenshot we saw earlier, but specifically just the transcribe deep speech component from our Docker Compose file. And this is how it maps to the RxJS code. So this particular pipeline code is actually the same for each component. And it takes whatever the input is. So the input described here is S3. It then gets the samples from that input. It then loads those samples before transforming them with whatever the transform has been prescribed, which in this case is deep speech, and then saves them to the output, which again in this case is S3. If you don't know TypeScript or JavaScript, don't worry. All you really need to note here is that each component runs the following cycle: load the data, run the transform, save the data. Now that's pretty much it for our design decisions. So now I'm going to talk through some of the types and interfaces I built to help me accomplish this system. So first up, and arguably less important, is our data types. So firstly, everything is a sample in our system. The sample interface ensures that we keep track of which processes the sample has undergone. It provides our data lineage. The sample interface also prescribes a timestamp for all of our data in our system, because all of the data in our system refers to a particular minute. The other data types are all very simple too, just adding their relevant type and value to the underlying sample. So we can see that the audio segment data type extends the sample data type, providing the same properties, and then just adds in a thing called data, which happens to be a raw buffer. So that's the audio data. Whereas the transcript data type extends our sample, again, by providing a chain of processes that is undergone, the timestamp that it's referring to, and this time, the actual text of the transcript. The rest of these files have been cropped from the screenshots, but all they contain is just various serialization and deserialization methods to load in and out of our different file types. But there's no complex functionality because they all use open standards. Now, more importantly, our functional interfaces. These reside inside each component, and as I mentioned before, follow the general pattern of load the data, transform the data, save the data. Most, if not all, ML pipeline libraries and platforms will provide sources and sinks for you out of the box and just allow you to focus on writing the transformation logic. Quite often on larger teams, the transformer interface is where a line may be drawn between data scientists and ML engineers. For our radio example specifically, I've made these generic types, meaning that they can be combined with the previous data types we saw to create distinct types. So as an example, the source type is generic of anything that extends sample. So that means we can have a source for transcriptions, but we could also have a source for audio segments. And then much the same for sinks. We can have a sink that syncs audio segments or transcriptions or sentiment or topics mentioned. The transformer generic type actually takes in two different types as part of its generic arguments, and that is obviously the input type and the output type. So in the example of our speech-to-text component, the input type is the audio segment and the output type is a transcript. But in the case of our sentiment analysis, well, the input type becomes a transcript and our output type becomes sentiment. However, they all expose the same functions within. So we've got get samples, which simply returns purely the timestamp and the processes that timestamp has undergone, a load method to actually load the data. The sync just exposes a simple save method, and our transformer just provides a transform method that takes the input in the first type and then provides the output in the second type. It also has the process name attributed to it, which enforces that all of our transformations actually define the name of the process such that we can have that data lineage throughout. So these functional interfaces, the guiding principles and our design decisions really make up all you need to know to design your own ML pipeline from scratch. So I'll now quickly list off some of the implementations I wrote to fulfill these interface types. For the data implementation, so sources and sinks, we've got sources that poll S3 for MP3 files, as well as polling S3 for JSON transcripts. For the sinks, there was actually more because we had to both upload MP3s to S3 and transcripts to S3, but we also needed to insert our sentiment and topic output answers into Postgres. It's important to note that although these implementations simply poll S3, the actual interfaces don't restrict you to polling, right? So you could, if you wanted to, extend these implementations to actually connect to an SNS topic, for example, and then have a completely event-driven pipeline. In our case, however, as we know, we have a known cadence. We know that new files are only going to be every minute. It's very easy to poll at a slightly higher frequency than that minute, and we can actually run the whole system more efficiently because of that. For the speech-to-text implementations, I did 2 versions of an open source Mozilla DSpeech, version 0.6.1 and 0.7.3, as well as comparing the 3 major cloud providers. So the Azure Cognitive Services speech-to-text API, AWS Transcribe API, and Google Cloud Platform speech-to-text. Much the same for the text analytics implementations. For entity extraction, I use just a package available on NPM known as Compromise.js. And for the sentiment analysis, just a package on NPM known as Natural.js, while also comparing, again, the 3 major cloud text analytic API endpoints. And then combined with all that, it's just a simple Grafana dashboard to actually read out from that from the Postgres database that I was mentioning. And this is actually hosted live at the moment on radio.eliiza.ai, and it looks as depicted here. What I think is worth mentioning is that you can actually select the source as well as the speech-to-text component and the topics mentioned and the sentiment analysis components, so that we've actually passed through our data lineage all the way to the end of our pipeline, which makes it really easy to compare the different results across different components. Okay, let's have a quick review. How did we do? And I guess if you don't take anything else away from this talk, this is probably the slide that's worth taking away. We wanted an orchestrator that clearly composes our components and draws our data, and draws our DAG from data to answer. Well, our orchestrator could be clearer. Currently, to piece together, you have to piece together from both Docker Compose and the RxJS sort of implementation. However, relying on Docker Compose enabled us to just piggyback off that runtime, so we didn't have to write any new code to have an orchestrator. We wanted to have well-described interfaces between our components. Well, we saw that we had completely typed interfaces and data types for all of our components, so we definitely did that. We needed to have agreed points of ownership and responsibility for each component. Yeah, okay, each of our components had clearly defined responsibilities. We wanted our components to be generic enough for reuse as new questions arose. And I think we could say that we clearly saw how we were able to extend our pipeline as new questions arose. We also needed to have the ability to monitor, test, and compare performance of different versions. So it's one thing I didn't really touch on in this talk, but you could, I sort of mentioned at the end, you can select the different versions of the components in the dashboard to compare their results. It's also worth mentioning that because we just used Docker Compose as our orchestrator runtime, you can use any off-the-shelf monitoring solution that's been designed for containers to get live monitoring of that system. And then we also needed to support version data or data lineage. And we saw how we were able to support that with our versioned processes prefix in our data lake. I guess a possible part 2 to this presentation that I'd like to do in the future is extending it to incorporate some ground truth data comparison. So at the moment, it just runs on live radio, which means that we don't really have a metric for what is a truthful transcription, or what is a truthful analysis of sentiment or topics mentioned. But you could run this system with different input data. So if you had something where you did have a known transcription or a known sentiment, you could just pass that into the input and get that ground truth data comparison there. Excuse me. Another thing, as I mentioned at the start, is we're only focused on the inference side of our ML pipeline. So it'd be great to extend this to cover some of the components you may need for the training side of ML processes. But I also really want to highlight that although this wasn't covered in this talk, all of the guiding principles that I went through and those design decisions still apply. And then other next steps that I guess are more general that I'd like to take is I'd really like to open source this code. That one's really on me, just to go back and clean up the repo. It's a bit of a mess at the moment. I'd like to integrate some of the monitoring out of the box. It'd be quite easy to extend the language support. So Python, everyone loves coding in Python, so that's probably the next one to extend it to. And we could also move to a standalone orchestrator. With that said, that pretty much brings it to the end of the presentation. Is there any questions? Okay, well, feel free to think of some questions. In the meantime, I have some interesting results that are worth sharing. So this is essentially running every possible combination of speech-to-text component in combination with every other possible combination of transcript-to-sentiment component. And unfortunately, they didn't all fit in the screenshot, but you can see here, it's this particular color refers to AWS transcribe as the speech-to-text before being passed into AWS comprehend as the text-to-sentiment. And we've got a bunch of different combinations. But the main takeaway here, I guess, that I wanted to highlight is just that you can see how varied these results are. So this was all run on the same piece of audio as an input. And then you can see at certain points in time, so for example, maybe here, 5.9, they generally agree. But at different point, at 15 minutes past 5, they strongly disagree. So there's some combinations that are very confident that this is a negative sentiment in this minute. There is a different combination that thinks that there's a very positive sentiment, and there's even some that think that this is quite an apathetic minute of radio. So I just thought that was worth sharing. Another one that's worth sharing is again a similar thing, but this time with the topics that were mentioned with that entity extraction component. And this specifically is just for the word Australia. And the one that I really like about this is that you can see that even on the same piece of text, so these bottom 4, for example, the transcription text was the same. So it's all being processed by GCP speech-to-text. The different entity extraction APIs actually counted the word Australia different numbers of times, right? So GCP language was confident that Australia was actually mentioned twice, but everyone else only thought that it was mentioned once. So again, I'm not sure how much you can draw from that other than just there's a high degree of variance in these systems.
So
in for questions?
I have a question.
Yes.
If you have everything like you have ordered it here, if a new topic were to come up, for example, what we saw earlier in one of the screens, that Victoria was labeled as a person, how quickly can you redeploy everything?
Yeah. So yeah, I guess 2 things worth mentioning there. The category. So which one is it? The category is much more accurate on the cloud APIs than it is in the open source. So this is just using the open source compromise.js library, which is just a hard-coded dictionary of words with categories applied, which is why it thinks Victoria is a person. The cloud APIs are much better at actually determining a more relevant category. In terms of how quickly it is to redeploy that model, well, it's really quick, right? All you need to do essentially is package up your new model in whatever container you would like, and then add it back into. You can either add it and run it alongside as a new container, or you can just version. If you're sure that you want to replace whatever versions there, you can just version the existing one. So I guess one of the main benefits of this pipeline design is that you can have different version components running in parallel.
That would have been the next question. Yeah, thank you.
Yeah, so we can see here this particular view, which is the one that is running live on the website, actually has two different radios running in parallel. But then, of course, like this one was with all of those components running in parallel on just a single radio. So you can mix and match combinations of your components. Yeah, so how is this deployed? So again, this is, I guess, my main driving factors when making these decisions is I wanted it to be really first principles. So in terms of how this is deployed, it's Docker Compose up with that Docker Compose file. You can wrap that in whatever CI/CD you would like. Is the process of creating managing directories in the S3 as the components version updated done by the CI? So the process of creating and managing the directories is actually completely handled by whatever you specify here as the source. So sort of the code within that get data, transform data, save data process, that transformation uses whatever process it's been labeled with. And in this case, the label is also the name of the component you want to run. So by specifying ffmpeg, you're saying that that the output to this component is going to be labeled with ffmpeg, and you can see that as it's the input to this component becomes the combination of these two, and the same thing happens here, where the input to the final component becomes the combination of whatever the input to the previous component was plus the versioned process of that component. When you mentioned direct data lake integration, does that mean you keep a serialized data set to train off for future analysis? Keep a serialized data set. Yeah, so each stage is completely kept just in S3. For this particular example, I've actually just got I forget, it's either 1 week or 2 week. Things get deleted after either 1 week or 2 week, just to keep costs low, but you can keep it in there as long as you'd like. And that's, yeah, it is serialized in there in terms of it. There are MP3 files and JSON files, but you can also keep your raw data in there if you wanted to. I mean, our MP3 files are effectively our raw data in this case. If training, how do you manage the size as the lake grows and slows down? Yeah, I mean, I guess, I don't know if that's specific to the training aspect. It's more just how do you manage the size of a data lake as it grows? I think that's an open-ended question, right? You need to just determine whatever implementation you're going to use for your data lake needs to incorporate how much data you think your problem is going to, or your platform is going to handle. If it is, so it's not used, yeah, so this example is not used for training. I guess why the data lake is because you can still use it for rerunning previous examples and doing that comparison, as well as just general debugging, right? So if you suddenly see, I don't know, like all zeros, like this is just a flat line on your output, and you want to know why that is, well, you can just open up the S3 browser and hop in to whatever data that's reporting as and read the transcript yourself and go, okay, maybe our transcript is all null values. And then you know that, okay, you need to move back a step further. Well, what is the raw audio? Maybe it's not being recorded properly. All right, well, thanks everyone. If you want to discuss the power of machine learning pipelines and how Eliiza can help you harness them, feel free to further email me. That is my email address. You can also Again, as I mentioned at the start, feel free to reach out to info@eliiza.com.au if you're interested in having some of these talks or presentations more specific to you or you and your team. And yeah, thanks again.
Another question